Hello. First of all, there was a wrong sign at the end of last lecture. I would like to fix at some point at the end, more or less. We were considering this function here, minus the logarithmic derivative of the zeta function. Okay, the zeta function has a pole at a pole of order 1 at the point zeta equal 1. So if it has a pole of order 1, okay, independently of the residue of the pole, near this pole we have this minus plus, let's say, plus some holomorphic function. So the Laurent expansion of this logarithmic derivative begins like this. It's only because of the fact that it has a pole of order 1. So if we take the sinus, we change the sinus here, we have this. And we have, of course, that minus z prime over z minus 1 over z minus 1 is a holomorphic function that, in fact, this holomorphic function has no zeros on the, as the denominator has no zeros on the straight line, vertical line, real of z equal to 1, can be extended to a neighborhood of this straight line here. Well, in fact, far beyond, of course, but we only need that it can be extended. So the correct sign like this, but this was what we needed, in fact, because we have that this expression here is z times 1 to infinity of phi of x, phi of t minus z minus 1. T in this was called g. Okay, and the statement of last results said us that if g minus c minus 1 could be analytically continued, etc., etc., then the limit of phi of x over x is equal to c, and it is exactly what we have here. G is this function here, minus c is equal to 1. Okay, it has nothing to do with the fact that the residue is 1, but with the fact that you have a simple pole at the point 1. Okay, so the conditions are correct, but at some moment I put here a plus or something like this morning in the last session. So I would like to fix that before continuing. Okay, so after fixing that, we begin with the 23rd session. I think 23rd session, and in this session and the following sessions, I only would like to make a short introduction to the theory of elliptic functions. The theory of elliptic functions. Okay. Well, I'm going to motivate a little bit some of the things that we have. Elliptic functions are a class of special functions that appear in many contexts in mathematics. Let's say they appear, for instance, as some solution of certain integrals. They appear when you try, for instance, to develop formulas related with the length of an ellipse. So they obtain the name because of that. We appear naturally in the context of algebraic geometry when trying to study which are called elliptic curves, which are curves of genus 1, and plane curves of genus 1, if they are, let's say, non-singular, are cubic curves. So we will make some connection about cubic curves, and it has some connections with some other subjects in mathematics. Okay, so it's even if it seems to be a very specific subject, and in fact it is, but the application in many branches of mathematics is quite important. Okay, let's motivate with something. For instance, everyone knows about Pythagorean triples. What is a Pythagorean triple? Pythagorean triple would be a triple of natural numbers like this, such that p squared plus q squared is equal to r squared. Okay? Everyone knows that there are many of them. For instance, the most well-known one is so Pythagorean triples corresponds, of course, to right triangles having integer sides. Okay, how can we find all Pythagorean triples? Okay, the fact we have a Pythagorean triples, we know that p over r, the square. So the task of finding Pythagorean triples is the same task of finding rational points on a circle. So which points on a circle have rational coordinates? How can we find that? Okay, let's draw the unit circle. Imagine that we have a point here having rational coordinates. Okay, and take for instance this point here, 1, 0. Okay. These 2 points have rational coordinates, so the slope of the straight line through these 2 points have also rational coordinates, and this line here, for instance, cuts the vertical line in a point of rational coordinates. So we could try to parameterize these points by the points of this vertical axis having rational coordinates. So take a point here, 0t, where t is rational. T is rational, and take the straight line that which joins this point 0t with 1, 0. This straight line has this equation, as everyone knows, and cut this line with the unit circle x squared plus y squared equal to 1. So it would be x squared would be 1 minus y over t squared plus y squared equal to 1. Okay, so we have here 1 plus y squared times t squared minus 2 times y over t plus y squared equal to 1. 1 cancels with 1 here, and so we have something like y squared 1 plus t squared minus 2ty equal to 0, multiplied by t squared, everything. Okay, there is a solution, y equal to 0, that of course corresponds to this point here. This is not an interesting solution, we're interested in the other solution. The other solution corresponds to y equal to t, which is rational. Okay, and if we know such y, we know that x is 1 minus y over t, 1 minus 2, 1 plus t squared, so it would be 1 plus t squared minus 2 minus 1 plus t squared, 1 plus t squared. So the points with rational coordinates are the points t squared minus 1, I'm going to write like this, t squared plus 1, 2t, t squared plus 1, which are rational. So in this manner, we can find all points with rational coordinates over the unit circle, and from that, all Pythagorean triples. In order to do that, the success is guaranteed because of the fact that a circle can be parameterized with rational functions. Okay, it is always possible to parameterize a circle using rational functions. So, something like this. It is possible to parameterize a circle using rational functions, and it is true because of the fact that you fix a point on a circle, a point with rational coordinates, and you take a straight line. This straight line cuts the circle in only another point, because the circle is a curve of degree 2. So, and this cuts in exactly another rational point. You have to solve finally some order 1, degree 1 equation, degree 1 algebraic equation. So solutions are in the field of rational. You don't need to escape your field in some sense. Okay, but these curves having this property that can be parameterized using rational function are called in algebraic geometry rational curves. They are not only, let's say, only circles. For instance, every conic is a rational curve, but there are more rational curves, having perhaps singular points. For instance, the cusp, which has the equation y squared equals to x cubed. Of course, it can be parameterized as x is t squared and y is t to the 3, so it can be parameterized easily using only polynomials in this case, so it is also a rational curve. Okay, but not every curve is rational. In fact, if you take a curve of, for instance, of degree 3, without singular points, this is the curve of degree 3, but it has a singular point here. Perhaps I will say some words about that in the last lecture. If we take a curve with a degree 3 curve, perhaps without singular points, it cannot be parameterized using rational functions. So you could ask a question, so can I parameterize using another kind of functions this curve? Any cubic curve, for instance, can it be parameterized? So we will see that yes, it can be parameterized using another kind of functions, which are going to be these elliptic functions here. So it's one of the motivations of trying to study curves that are not rational. Of course, it could be extended to higher degree curves. This kind of arguments. Okay. Then, so let us introduce in a different manner these curves. For that, we are going to introduce elliptic functions through the theory of periodic functions. So, if you have a function on C, in general a meromorphic function, consider a meromorphic function defined on the whole plane. Okay? So we will say that the number omega is a period of f if, of course, f plus. For every z, we have this equality. Okay? The set of periods, we are going to denote it, for instance, at least for a moment, we will denote like this the set of periods of a curve. Of course, it can be empty. But if it's not empty, we are going to study this set. This set is, of course, a group. In fact, it's a Z module, because, of course, the sum of two periods is again a period. Or if you multiply a period by an integer number, you obtain again a period. So, in fact, it's a Z module, so it's an abelian group, an abelian subgroup of C. Can it have, let's say, accumulation points? Well, no. If a set of periods would have some accumulation points, you would have a sequence of points where the function have the same value. And if such sequence of points has an accumulation point, the function would be constant. So, except in the trivial case where f is constant, P does not have accumulation points. So, P is a discrete group. So, it's a discrete Z module of C. How is this discrete group? So, we want to see that, in fact, P is generated by at most two elements. P is generated by at most 2 elements. Okay? Well, assume, of course, that it is not empty. So if it's not empty, if it's not 0, I mean, for instance, 0, of course, it's always a period. When I say it's not empty, I mean that the set of periods is, there is at least one non-zero period. Okay, so as it is discrete, take a period of a smaller modulus. So take omega 1, some period, having the smaller possible modulus. So for every other non-zero period, the modulus of omega is greater or equal than omega 1. Okay. Well, of course, all the numbers n omega 1 are also period. Assume there is a period on the same line. So we have on the same real line, you have some omega 1 here. Consider this line. So we are going to see how are the periods, the possible periods over this line. Assume you have some period of the lambda omega 1 where lambda a real number. Okay? If lambda is not an integer, we could decompose this period as the integer part of lambda plus the imaginary part. Let us write like this. This would be a period, and as these products of integers times omega 1 are always periods, if this is a period, this would also be a period, but this has module smaller, because the module is, and this is strictly smaller than omega 1 if lambda is not integer. If lambda is not integer, and it's not possible. So, well, the only periods, the possible periods over this line are the integer multiples of omega 1. So, we have this, we are going to call P1, the set of n omega 1, are the only possible periods over this line. So, two possibilities may arise. First of all is that P1 is equal to P. So, we have finished. If P1 is equal to P, we have found all periods. All periods are generated by one element. Okay, and our result is done. Assume, on the contrary, that P1 is not equal to P. So P minus P1 is not empty. So if P minus P1 is not empty, take an element on P minus P1 of a smaller possible modulus. For a smaller possible modulus, okay? So it's an element which is not in the same real line as omega 1, and which has a smaller possible modulus. Okay, and consider P2, the lattice, the Z module generated by omega 1 and omega 2. I mean the set of all n1 omega 1 plus n2 omega 2, where n1 and 2 are integers. Okay. Two possibilities. Either P2 is equal to P, we are done, or perhaps not. Assume that is not the case. So assume that P minus P2 is not empty. Take an element, omega, which is not in which is in P, and is not in P2. Take such an element omega. Well, as omega 1 and omega 2 are not in the same line, they generate C as a real vector space, as C is a two-dimensional vector space. So omega 1 and omega 2 are bases. So such an omega can always be written as A omega 1 plus B omega 2, where A and B are real numbers. Okay. We can remove some integer parts of these A and B. We can cancel some integer parts, and adding some element of this kind here, we could, and we still are in the set P, we could assume that A and B have absolute values that at most 1 over 2, 1/2, adding some integer multiple of omega 1 and omega 2. Okay? We can assume that. So, now as we can assume that, now take the modulus of omega. As omega 1 and omega 2 are not collinear, the, let's say the triangular inequality is strict. So this is strictly smaller than strictly smaller, and this would be smaller or equal than 1 over 2, and omega 2 in modulus is bigger than omega 1, so this is, so omega would be in modulus strictly smaller than omega 2, and this is a contradiction, as we have chosen omega 2 as the element with minimum possible modulus. So this case is not possible. So finally, we have obtained that the set of periods is generated by 1 or 2 elements. Okay, this in fact is a much more general result. In Rn, any discrete submodule is generated by at most n elements. This is a quite useful result, also some in number theory also for that can be used for this result, and it also can be deduced from the theory of modules. For instance, if we already knew that the set of periods, which is a Z module, is finitely generated as a Z module, every finitely generated Z module can be classified easily using the torsion elements, etc. So any finitely generated Z module without torsion, and this here has no torsion because it's a submodule of Rn, so it cannot have torsion, is free. So automatically from the beginning it's free, and we could also know that the dimension must be strictly, or at most, the dimension of this n here. So using those algebraic facts, we could have arrived to a similar conclusion. But very quickly we can arrive to this conclusion using these arguments here. Okay. So the set of periods is generated by either one or two periods. In the case of one period, well, assume that the set of periods is generated by only one period. And consider such a function, a periodic function having the set of periods generated by this omega here. So if you take f log t, if you take this function, this is a well-defined function. Well-defined function using the different, take any determination of log t, and this can be correctly defined because of the periodicity of f. So this is a well-defined function, and in fact this defines, for instance, assume this is holomorphic, assume your function f is holomorphic, so this is a holomorphic function over c bar. T, here this function is not defined at 0, over c bar. So a holomorphic function on c bar, on C star, sorry, on C minus 0, has a Laurent expansion. So this function has some Laurent expansion like this. A two-tailed expansion with perhaps an infinite number of terms with a negative exponent. And from here, this is Z. So if Z is all that, 2 pi I omega z is equal to log t, so t is the exponential of this number, so our function f of z can be written like this: the exponential of 2 pi I n z. So it can be developed in a series of exponentials, a Fourier expansion. Okay, like this. Well, this is a subject different of the subject we are going to study here. So this would be for functions having the set of periods generated by one element. So let us consider doubly periodic functions. We are interested in the case of doubly periodic functions. So periodic holomorphic or meromorphic functions whose set of periods is generated by two elements, omega 1 and omega 2. Okay. First of all, a useful remark. Assume that the function would be holomorphic. So assume you have a holomorphic function whose set of periods is generated by two periods like this. What can we say about this function? So very few things can be said because of the following fact. Consider this parallelogram here and consider the tiling of C by parallelograms of the same size. Zero here. Okay. If the function is holomorphic and periodic, consider this parallelogram here, consider the closure of the parallelogram. This is a compact set, and everywhere the function assumes exactly the same values than in this compact set. Okay? Why? Well, you take a point here. By periodicity, the value that the function assumes here is the same that the value that assumes here. So all the values the function assumes are the values that it assumes on this parallelogram, and as this parallelogram is a compact, the function is bounded on this parallelogram. So by Liouville's theorem, f must be constant. So every doubly periodic holomorphic function is constant. So, well, the interest is not so big. Okay, so only constant functions can be studied here. So we will be more interested in meromorphic functions. Meromorphic functions, doubly periodic meromorphic functions. So it will be our subject. In general, a doubly periodic meromorphic function is what will be called an elliptic function. Some other remark. The set of periods, the set of generators of the periods is not at all unique. It's not at all unique. So we have a set of generators like this. This is a basis of a Z module. Another basis of this same module using a little linear algebra could be obtained from this basis using an invertible matrix. So if you take an invertible matrix, A, B, C, D, invertible over Z, so if it's invertible over Z, this is a 2 by 2 matrix invertible over Z. So a matrix of integer numbers such that the determinant AD minus BC is equal to plus or minus 1. Okay, you have another basis. So any other basis can be obtained like this. Where A, B, C, and D integer numbers satisfying this relation, AD minus BC equal to plus or minus 1. So, of course, the set of generators is not at all unique. Can be constructed some kind of canonical or more or less canonical set of generators, or at least more or less useful set of generators in the following way. For such a set of generators, omega 1 and omega 2, a number that is going to be important is in fact the quotient of these two, T. We're going to call T to this quotient of these two generators. Okay, this quotient satisfies several properties. For instance, t in module is greater than 1. First properties. Second, well, we can choose omega 2 in such a way that the imaginary part of t is positive. Well, if not, if it's negative, we only have to change omega 2 by minus omega 2. And we arrive to this condition. So we can assume that t is in module greater than 1 and the imaginary part of t is positive. Moreover, let us consider the number, for instance, let me have a look. Yes, as we know that omega 2, by the choices of omega 2 as the minimum, etc., is smaller or equal than omega 1 plus omega 2, and omega 2 is also smaller or equal than this number, from here, dividing by omega 1, you will obtain that modulus of t is smaller or equal than 1 over plus t, and smaller or equal than 1 minus t. So t is closer to 0 than 1 or than minus 1. If it is closer to 0 than 1 or than minus 1, t is necessarily here. So from this, we can assume that the real part of t is at most 1 over 2. Okay, we know that. And well, in fact, if it was minus 1 over 2, we could change, t by t plus 1, the same as changing omega by omega plus omega 1. You can verify that conditions are not changed, and we could assume that in fact that the real part of t is not here. So for the moment t is in the upper half plane, outside the circle of degree of radius 1, and here we have, so t must be here. Not here, it could be here, it could be here, or it could be here. So t is a point that could be here. Tau is a point that could be here. And well, moreover, if tau was here, so if real part of, if imaginary of part of t is equal to 1, if imaginary part of tau is equal to 1, okay, we could change the set omega 1, omega 2. In this case, omega 1 and omega 2 have the same modulus. So we could have changed omega 2 at the beginning. So we can change by minus omega 2, omega 1. So change the order like this. What we are we winning something with that? Okay, see, we take this quotient now. This quotient would be minus 1 over tau. This is, as tau is of modulus equal to 1, this is minus the conjugate of tau. So if we take a point here, we will have its conjugate here and its opposite here. We are in this point. Okay, so we can assume that tau is not here. So, in fact, could assume that tau is, erase this, it's in the interior of the set, or perhaps over this part of the border. And this is a kind of unicity, canonicity of this number tau, related with the lattice, with the set of periods of the function. Remark that if you change arbitrarily like this your set of periods, you lose all these properties. You lose, for instance, the fact that let's say that omega 1 is the element with a smaller possible modulus, etc. But if you take into account these conditions, you can arrive to some canonical, in some sense, some canonical representation, some canonical set of periods. Okay, so if necessary, we could assume that in the sequel. At some moment, perhaps, it could be useful. Okay. So we have our set of periods, and we have this drawing. We are going to call, if we take some point omega on the plane, we are going to denote as delta omega what is called a fundamental parallelogram with vertex omega. It could be the set of points omega plus t1 omega 1 plus t2 omega 2, where t1 and t2 are between 0 and 1, closed on 0 and open on 1. So we have something like this. Take a color chalk, take a point here, so something like this. And the interior. Okay? By the double periodicity, what happens in any fundamental parallelogram is the same that what happens everywhere. So in order to study the behavior of any elliptic function, we only have to study the behavior on any fundamental parallelogram. After that, it replies. The function is replicated everywhere. Okay? So these fundamental parallelograms are the good domains to study functions. Okay. By the way, I'm not going to speak about that. There is a geometrical way of having a look to this function. It is the following. Okay, the function is repeated everywhere, so we have only some interest in this parallelogram. So we could identify all these parallelograms. You identify all these parallelograms from C. Identifying these parallelograms, I mean, you take a parallelogram, for instance, identify this side with this side and this side with this side. What do you have? You have a torus. You have a torus like this, and what you have is a function defined on a torus with values on the Riemann sphere. So an elliptic function, in fact, is a function between these two Riemann surfaces, a torus and the Riemann sphere. So it could be studied geometrically like this. Okay? Now, are all torus similar? Well, the answer is no. Similar in which sense? Of course, all torus are similar from a topological point of view. Such a parallelogram is equivalent, is topologically to a square, let's say, and well, every torus like this, so it doesn't matter which lattice, which set of periods you have. But analytically, it's not true that two torus are equivalent. I mean, they are not, the torus you obtain from two different sets of periods, two different lattices, there is not a biholomorphism between them, not necessarily. Okay, so from an analytical point of view, torus, or not all toruses are the same. From a topological point of view, yes, but not from an analytical point of view. But anyway, could be studied like this. Okay, in fact, if you take any Riemann surface that topologically is a torus, it comes always a function like this. It comes from a function defined on a lattice, because you could take the universal covering of this torus. The universal covering of a torus is, of course, C, and the covering map from this universal covering over the torus is holomorphic. So you will have something like this. So it's the same to study these objects and to study this kind of functions, this function defined here. It is the same. This is, let's say, a more geometrical point of view, and we will adopt now a slightly more analytic point of view. Okay? So we need only to study to study analytical properties of elliptic functions. We only need to study their behavior on a fundamental parallelogram. And there are some interesting results that are in the following. Results sometimes called Liouville theorems. Well, first of all, assume you have an elliptic function and take a fundamental parallelogram. This is a meromorphic function. So on a fundamental parallelogram, it has some poles. There are some poles. If you take the sum of the order of all poles on a fundamental parallelogram, you obtain some number, some natural, strictly positive natural number, that is going to be called the order of f. So the order of an elliptic function would be, by definition, the sum of the orders of all the poles f has in any fundamental parallelogram. By previous considerations, it is independent on the fundamental parallelogram you choose. Okay? Let's call it order of f. So first of these Liouville theorems says that if you take a fundamental parallelogram, so first result, theorem 1, if you take such a fundamental parallelogram, you take all the poles and you sum all the residues, the sum is 0. The sum of residues is 0 on a fundamental parallelogram of any elliptic function. Why? This is quite easy. Take a fundamental parallelogram and, well, as you can choose your fundamental parallelogram, move it a little bit if you need, so in order that you don't have poles on the border. You can always move it a little bit. So take a fundamental parallelogram without poles on the border of the parallelogram. Okay? So you have your poles somewhere inside. Okay? And you take the integral along. I'm going to write like gamma 3 in this order and gamma 4 in this order. But anyway, the border, you could represent as gamma 1 plus gamma 2 minus gamma 3 minus gamma 4. So this is the border, gamma, and you take the integral 1 over 2 pi I gamma of f. By residue theorem, this integral would be the sum of the residues at all the points inside. But if you consider, for instance, gamma 1 and gamma 3, which is the integral along gamma 3 of f of t? Well, this is the same as the integral. This point here is omega plus omega 1. Here is omega plus omega 2. Omega. Okay, this is the same as f of t plus omega 2 along here with a change of variable, small change of variables. And by periodicity, this is f, the integral of f. So the integral along gamma 1 is the same as the integral along gamma 3. So the integral along gamma 1 and minus gamma 3 cancels. Gamma 2 minus gamma 4 cancels, so this integral is 0. So the sum of all the residues is 0. Okay? This has an immediate consequence, that is that the order of any elliptic function must be at least 2. Because if the order was 1, what does it mean? The order is 1, the only possibility is that you had only one simple pole. One simple pole. And if you have one simple pole, this simple pole has a non-zero residue. Every simple pole, if it is a pole of order 1, that must have some non-zero residue, and this is not possible. So the order of any elliptic function must be at least 2. If it is 2, there are two different possibilities. Either on any fundamental parallelogram you have 2 poles of order 1, or you have 1 pole of order 2. There are the two possibilities. And if the order is greater, you have many other possibilities, of course. Okay, this would be the first Liouville's theorem. I state perhaps the second one, and I think I will stop here. Second Liouville theorem says that each point is taken the same number of each value. If you have some elliptic function f, f takes every value c the same number of times. So this would be theorem 2. F takes every value of C as many times as the order. As many times as the order. Okay? And for that, it's enough to apply the previous result about the sum of the residues to the following function. You consider, take some value c, and you consider this function f prime of z over fz minus c. This would be a periodic function, a doubly periodic function also, and as the sum of the residues is 0, the residues here have to do with the number, the points where f must be either with the points where f takes the value z, or either with the poles. So it says that the sum of the order of the poles minus, for instance, the sum of the orders of the c values of the function must be 0. So applying theorem 1 to this function here, we obtain that every value c is taken exactly as many times as the order of the function. So in particular, every function c seen also as a map between these two Riemann series must be, of course, surjective. It is function here. It's always surjective, and not only surjective, but if you take any point here, the number of its counter images is always the same. It's like a covering in some sense. It's not exactly a covering. There are some points, of course, that are the images of some multiple points, that singular points. So this point perhaps, but generically, for instance, if the order is 2, for each point, it comes from 2 points here. It may happen that for some finite number, comes only for 1 point, that is a double point, are the critical points in this of this map. But generically, we have the same number of points. So this would be the second. This could be the second Liouville theorem. Every value is taken 2 times. So, and I think I stop here, and in the next session I will continue with developing the theory of elliptic functions. Thank you.